All right, welcome to The Explainer. We're about to jump into something huge, something that's both incredibly exciting and honestly a little bit scary. We're talking about teaching AI the language of our own bodies, the language of health, and it's a mission where getting it right is everything. So, to really get a grip on this, you've got to start here. This Richard Dawkins quote just nails it. Physics, he says that's the simple stuff. Biology, now that's the study of the really complex things. And he's so right. Our bodies aren't like simple machines with predictable rules. They're this beautiful, messy, complicated universe. And that is why teaching a computer about medicine is so incredibly hard.
Okay, so you've got this super complex field and you're trying to inject AI into it. What happens? Well, you get this massive potential for good, but also this huge potential for things to go very wrong. It's truly two sides of the same coin. Look, on the one hand, the promise here is just wow. Imagine an AI that could catch cancer years earlier or tailor a treatment plan just for you, right down to your DNA. It could literally save lives and money. But, and this is a huge but, the flip side is terrifying. These AI models can pick up on biases we don't even know are in the data. They can be black boxes we can't understand. And if one of them makes a mistake, well, we're not talking about a weird movie recommendation. We're talking about deadly errors. And this isn't just me being dramatic. This is a real-world example. A few years back, researchers built an AI to predict who was at the highest risk from pneumonia. And it learned something completely backwards and, frankly, dangerous. It decided that having asthma actually lowered your risk of dying from pneumonia, which, as any doctor will tell you, is the exact opposite of reality. So what happened? How could it get something so fundamentally wrong? It's a classic case of the AI being smart but not wise. See, in the real world, when a patient with asthma gets pneumonia, doctors know it's serious. They jump on it. Those patients get more intensive care, they get sent to the ICU. The AI didn't see any of that. All it saw was a simple pattern. Asthma patient, better outcome. It completely missed the why, the human intervention. It saw the data, but it had zero understanding of the real-world context. And that story right there gets to the absolute heart of the matter. The problem isn't always the AI algorithm itself. It's the data we feed it. You could say healthcare has a huge language barrier. The fancy word for this is interoperability. It sounds complicated, but think of it like this. You and I can both have phones and we can send text messages back and forth. That's exchanging information. But what if my phone is in English and yours is in a language I don't speak? We're exchanging data, but we can't use it. We don't understand each other. That's the problem in healthcare. It's not about just swapping files. It's about being able to use that information because you understand its meaning. Let me give you some real examples. A doctor in one hospital writes down myocardial infarction. Down the street at a clinic, another doctor writes heart attack. Now, you and I know that's the same thing, but does a computer? No way. Or check this out, a real drug, pioglitazone. One study says no increased cancer risk. Another study says, actually, yes, there is an increased cancer risk. How is an AI supposed to make sense of that? It's chaos. So this is it. This is the big question. How do we get a computer to understand that all these different words, all these conflicting records, are actually talking about the same thing? Before we can even dream of a smart medical AI, we have to solve this language problem first. The answer really is to build a kind of digital Rosetta Stone for medicine. A universal translator that can look at all these different languages, myocardial infarction, heart attack, and know they all mean the same thing. And you don't get there all at once. There are levels to this. The first step, just getting systems to exchange information, that's the easy part. That's just plugging in the cable. The real challenge is the second step, semantic interoperability. That's making sure the meaning gets across. It's the difference between just hearing a stream of French words versus actually understanding what the person is saying. So how do we do that? Well, a massive part of the solution is this thing called SNOMED-CT. The simplest way to think about it is like a universal dictionary for medicine. It takes a concept like heart attack and gives it one single unique code. It does this for millions of things: diseases, symptoms, drugs, procedures. Everything gets a code, so a computer knows exactly what you're talking about no matter what words a human used. And listen, this wasn't something a tech startup built last year. This has been in the works for decades. It started all the way back in 1965. It was just a group of pathologists trying to agree on how to name things. And over half a century, it has grown into this enormous global standard. That long history is why it's so trusted and why it can be the foundation for all this.
Okay, so let's say we have our universal dictionary, our SNOMED. We've solved the what problem. Now comes the next big hurdle, teaching the machine how to actually read and understand human language with all its nuance and context. The old way of doing this was, well, kind of dumb. It was called a bag of words. It literally just put all the words from a document into a virtual bag and counted them. That's it. To this system, dog bites man and man bites dog are almost the same sentence, same words, right? But the meaning is totally different. Today's methods are way, way smarter. They use something called word embeddings, which capture the relationships between words, and it's all based on this one really elegant idea. You are known by the company you keep. The same is true for words. The AI looks at millions of sentences and notices that words like doctor, nurse, and hospital tend to show up near each other. So it figures out, hey, these words must be related. It learns meaning from context. This is where it gets kind of mind-blowing. Because the AI has turned words into math, you can literally do algebra with concepts. So check out this famous example. What happens if you take the idea of king, subtract man, and then add woman? Queen. The computer figures it out. It has learned the abstract concepts of royalty and gender, all on its own, just by reading text. It's incredible. Now, just think about applying that kind of power to the complex world of medicine. So let's put the pieces together. You've got a universal language for medicine, and you have an AI that can understand the nuance of that language. This is where we start to see what the future of health AI really looks like. But look, building this future isn't going to happen with one magic bullet. It's a huge project with a lot of different parts. This course breakdown is a pretty good metaphor for it. You can't just cram for the final and expect to pass. You need to do the homework, the quizzes, the project, everything. And it's the same with health AI. You need the data standards, you need the smart algorithms, you need the doctors to validate it, you need safety rules, you need the whole package, or it just won't work. And all of this work leads us to one final, incredibly exciting question. Once we get this right, once our machines can finally, truly understand the language of our health, what should we ask them first? What are the biggest mysteries we could finally solve? That's the future we're building right now.